Hi, my name is Albert Dunford, and in this tutorial video we are going to do a three-phase inverter. We're going to close the loop with DQ control, and then we'll set it up to be a gridley converter at the end. So getting straight into things, this is our inverter here, so just a simple 6-switch three-phase inverter. We're driving an RL load. We are looking and monitoring the three-phase currents right now, so IA, IB, IC. And then because this is going to be digital control, I am sampling those with these zero to hold elements. So we're sampling at 20 kilohertz, which is also the same speed as our switching. Moving through here, so the currents are being sampled, and they are coming down into this ABCDQO transformation. And we can have a little look at what that is doing. So here's the math. So we're doing a transformation flag of 0. So we have our equations that we're working through here. And then, so this is for the feedback. And then here we've got our, so this is an open loop to start with. So we're pushing in a D reference of 0.1 and a Q reference of 0. And the 0 sequence reference is 0 as well. And then we're just driving in. We'll pull up VMA here. Make that over there. And then we're delaying. So this is important. This delay element is simulating our digital delay of an MCU working or CPU, where you can only update the PWM duty cycle at the beginning of the next period, and then switching at 20 kilohertz. And so then we're coming up and we're driving all of these switches. I don't have dead time in this circuit. Simulating with dead time for control, it does nothing useful. All it does is derive a very small time step. If we're interested to see the impact of dead time, we can put that into another simulation, specifically to look at that sort of thing, but it does not help us with anything when we're just trying to close the loop. The last thing to look at is how theta is being developed down here. So we've got a base frequency, in this case it's 100 hertz. We're doing multiplying that by 2 pi, so omega equals 2 pi f. So then we're integrating that between 0 and 2 pi to get theta. And this is a resetting integral as well, so it's going from 0 to 2 pi and then resetting again. So we're just drawing a circle out, theta, and then that comes in and drives into these transformations here to get from ABC back to the DQ reference. Okay, so this is open loop, so we can simulate this, and we're going to see some three-phase currents. So here's the three-phase currents left over from that simulation. We can also have a quick peek at theta looks like. We can also have a quick peek at what the modulation of A looks like. So everything looks to be pretty happy here. Okay, so what we're going to do now, I'll also pull up what ID and IQ look like. So this is what the feedback values of ID and IQ look like. So what we're going to do is set this up so that we can monitor this or do a frequency sweep of this, and then we're going to use that frequency sweep information to close the loop. So let's set up the sweep. So what we need to do is we need to grab a AC sweep probe, and we're going to grab a multi-sign sweep block, and we're going to grab an addition block, and we're going to grab a sinusoidal input block. And these things we're going to put, AC sweep, we're going to look at what happens to ID. And then we're going to insert this sweep element into the ID reference right here. So in PSIM, when we do a frequency sweep, we're actually doing time domain simulations, so we can do this sort of thing. We don't need to worry about converting to an average model or doing any math to kind of figure out what this plant equations are going to be. That is completely not necessary. So all we need to do is introduce this perturbation and then pick the signal out where we want to look at. So this sweep is going to do, because we know the frequencies that we're putting in the phase, we can do an amplitude and gain comparison where we put the AC probe. So I'll link to some other videos that go into AC sweeps in detail, but that's not the purpose of this video. So there's other videos that cover how to do an AC sweep in detail. Okay. So all I need to know here is steady state time, so we'll call that 10 milliseconds. Steady state time, 10 milliseconds, V sine 1, plug that in there. These values don't matter for anything. We're switching at 20 kilohertz, so going up to about 7.5K is fast enough. We'll start relatively low as well, say 10 hertz. We don't need this many points, say 35. And our reference will start at 0.5, which is about 5% of what we had there. Actually, no, that's going to be 0.5. Okay, so we can just drive this now, and hopefully we get our frequency response. And this looks pretty good. We can take this and now take this into SmartCtrl. So what we'll do is we'll fire up SmartCtrl. Okay, so here's SmartCtrl. So we're going to import this frequency response from data at the bottom here. Click that. We're doing current mode control. Hit OK. Come in and grab this FRA file. So this is the default file. When you run an AC sweep, it automatically saves as this file format. Just hit open. Switching 20K. We can put our current here as 10. That's fine. Hit OK. Sensor. We can do a current sensor here. And let's just divide by 10. So we'll do an attenuation of 1 over 10. So that means that when we have a reference of 1, we'll end up with 10 amps on the output. We'll hit OK. Compensator will hit PI. So this, what we need to do here is define the gain of this system as 1. So to do that, we're going to put 1 and 0 here, and then we're just going to turn this into a ramp. So we'll do 50 micro, which is 1 over 20 kilohertz. And we'll hit OK, and we'll hit set, and we'll go here, and we can just now. So this is the SmartCtrl solution space. So we've got our green as our open loop transfer function, pink is the control to output transfer function. This is where you look for your cross frequency and phase margin, and then this is the solution space with the white being all of the stable cross frequencies and phase margins that we can work with, and reds are unstable. So we can just cruise around in here and find something that'll work for us. So maybe cross frequency of 500 hertz. Phase margin of 70 degrees will be good. Yeah, that's probably, we can go a little faster if we want to. 66 degrees, 470. So this, I mean, we don't need to, for this sort of system, we don't need to be, we don't need this, the bandwidth to be a particular number in order to be able to do like a 60 hertz signal or something like that. Remember, we're controlling a DC signal, and the sinusoidal aspect of it is sort of filtered away or taken away when we go into the DQ reference. So we don't need to have, in order to switch at like 100, to have like 100 hertz frequency, we don't need to have at least 100 hertz of bandwidth. This could work at lower frequencies. Okay, but we'll do this. This will be fun. So here's my KP and KI. So we're going to take these values back to PSIM. We just move this out of the way and move. We'll shut that down. We'll slide this over. We'll move this here. And we're going to add our PI control loop into this now. So I'm just going to extract this and put it over there, disable it. And we need to set up some difference elements. We need to grab a digital PI controller because we're doing a digital control. So we'll grab these two. And what these do is they do backwards Euler for us. So we just can put in the estimating coefficients, and then it'll do backwards Euler for us. We could, of course, use our S to Z converter here and do a conversion with bilinear. So implement one of those, but we're not going to do that. It's more blocks to put down. We'll just do this 928 milli. So that's this KP value I'm putting in right here. And then the time constant is going to be 349.983 micro. And then some sensible limits are probably -1 and 1. So this is important because it prevents anti-windup. And it also will prevent our system from going outside of the carrier envelope over here, which would not be good. So we can slide this over, And because the system is symmetric, we don't need to do a sweep for IQ. So we can use the ID value in here. And then you might also be thinking, well, is it okay to think that these are independent variables? And someone doing a PhD thesis might argue otherwise, but it's actually going to work out okay for us to just treat these as independent variables. There is some cross-coupling between the two variables, of course, but not enough for us to really care for this sort of thing. And I'm adding in these attenuation blocks. This is going to match that 1/10 that we did in SmartCtrl. So this is going to give us our attenuation that we designed for. So that's 1/10. Okay, so that we should be good to go here. And now we can add in our new reference. So we're going to have an IQ of 0. We're going to hold ID at 0. ID at 0. And we can do something with IQ if we like. So let's make that 1. And so we should see our 10 amps on the output. And we can run this. So ID and IQ should be 0 and 1, and they are. And then we can pull up our 3-phase currents, and we can see that that's at 10 amps. The amplitude of that is 10 amps. So there's that 1/10 working for us. And then so this is there's we would gain this because we did that 1/10 attenuation. So this is now equivalent to this 10x. So the peak of this. Okay, what else can we play with here? So we can actually confirm that that's the case. That we can confirm the SmartCtrl design numbers here for cross frequency and phase margin. So to do that, we would come in here, we would put another sweep setup, and in this case, we're going to be using this probe sweep, and we're going to set it up this way. Just copy these elements. And enable these ones. So what this sweep does now is this will do a control to output sweep for us. So this is different from that other sweep that we were using, which is this one down here. We're going to be doing this one, V sine 2, and we'll change this, V sine 2, that works. Again, these numbers here don't mean anything when we do the sweep. They will mean something in a time domain simulation, but they don't mean anything in a sweep. And we can keep these numbers, V sine 2. When do we hit steady state? Definitely by 10 milliseconds. And let's bump this up a little bit so there'll be a little bit more signal. And let's run the simulation. And here's our loop gain sweep. So there's a little bit of noise here. Okay, these are the settings that I decided to use for the loop gain sweep. Typically, for the loop gain, we need to maybe sometimes put a little bit more signal in. So when you're doing the open loop transfer function, 5 to 10% is a good number. In this case, I'm using 30% of what the expected ID value is going to be. So in this case, yeah, so we need a little bit more signal. And if we run this now, we can see what that loop gain will look like. And we can come in here. And so where the amplitude plot crosses 0, that's our cross frequency. And we can see that's right in the 420 hertz mark. SmartCtrl was telling us 476. You know, definitely we could be in that range depending on where we're going here. So very close to, which is good. These numbers are calculated with mathematical equations. This number is simulated with a time domain style simulation. So this number, if these are there's two separate ways of getting to these numbers, and if they're starting to look the same, then we're probably in really good shape. And our phase margin here is 180 minus 111, which gives us 69, which is close to the 66 that we were looking for. So it's 180 minus this 111. So everything looks pretty good. And the shape of this, if we compare to what SmartCtrl was telling us we were going to get, so if we slide that over there and just bring back this one now. So this is going to compare to the pink line. So we're definitely between 30 and 40 dB at close to 10 hertz. Phase is just above 100 and tailing off, and we're looking pretty good here with regards to comparison. So that's how we got to so we've got a working three-phase inverter now. So let me just disable that. Okay, so to check the performance of our controller here, to actually see it in like a time domain simulation, I just switch the constant source out with this changing square wave source, and we can run the simulation now. And so all the AC sweeps are switched off as well. And we can have a little look at what this will look like. Okay, so here's IQ, and we can see we're switching between 1.5 and 1 quite nicely, and the corresponding change in the current waveforms. So that all looks pretty good. Okay, so now let's get to the grid link part. So what we're going to do is connect this to a three-phase grid. So we will do that by going and adding in sources here. We'll add some voltage source, and we'll add a three-phase voltage source. So I'm going to add this in. And so this top signal, this top line is my A phase. So we'll just come over here and we'll drop this in. And I'm going to get rid of these resistors. We don't need them anymore. So keep those inductors for the smoothing, and we'll mix a lot of room there. So what we're going to do is now we need to sense the voltage here because we're going to want to synchronize our signal to be with we're going to need to change how our theta is generated to synchronize it with the grid. And to do that, we're going to use, this is going to be A, B, C, and we'll connect these all up to neutral. Don't ground this, otherwise you're going to be effectively shorting out the bottom side here because there's a ground over there. And then what we'll do is we'll do the exact. So what we need to do is find theta here. And how we're going to do that is we're going to use a Clark. We're going to go to alpha beta. So we're going to grab a Clark transformation. And we're going to use this. So this is A, B, and C. And then what we're going to do is, so alpha and beta, so A is essentially the real part, and B, beta is the imaginary part here. So what we can use is the arc tangent block, this guy right here. If we read what help does, the output of the arc2 tangent block is the inverse tangent of the ratio between the imaginary part and the real part of the input. The imaginary part being x and the imaginary part being y. So what we'll do here, okay, so the imaginary part is the y and the real part is the x. So we need to connect x and a. So we will flip this and flip it so that we've got x up here. So alpha goes to x, y goes to beta, and then this should be theta. So we can run this. Let's not run it quite just yet. So let's disable this guy down here. And this is going to be our new theta label, and theta. Oh, that's not quite connected. Okay, next we need to also discretize this. This is going to be still digital sampling, right? So we need to come in here. We need to sample these guys. And this is going to be at the 20K rate. Perfect. And then also let's check to make sure that our power is flowing the right direction. So we'll grab a watt meter. Plug that in. this is going to be power. And then we can also grab a VA meter as well. So we can look at three-phase, that the power factor and all that kind of stuff. So base frequency 60. This is at 60, perfect. We can push this up to say 240 volts. This voltage, line voltage, needs to be less than the DC bus over there in order for us to be able to push power towards it. Okay, I'm also going to switch off. So we've got our power meter. I'm also going to switch off the changing guy over here for now. And so this is at 0. And this is at 1. Okay, so let's run this now. We don't need to run for very long. We can look at ID and IQ, and they are settled. We can also look at power. This doesn't look to be quite right. And we'll get to that in a second. And we'll look at the VA, telling us 3 kilo. There's no power. Okay, so that means, so what we need to do here is we need to, now this is going to be our real power is going to come out of ID reference, and the imaginary reactive power will come from the IQ reference. So if we run this now, we can see that's exactly what's happening. Okay, so we've got our ID reference now. It looks as providing the real power, and our IQ reference is will be the reactive power. We can see the real power meter is now showing us 3 kilowatts, which is the same thing as what our VA meter is showing us. So our power factor should be 1. And then we can come in here and say, if we, this is by nature bidirectional. So if we push this to a -1 and we do this, we're going to see that the power should be negative. And it is, so there's -3K, but still with proper, so now with our -3K, but still a good power factor. And then we can also push, if we go 1 here, or let's just make it 0.5 and 0.5 there. So now we've got a little bit of reactive and real power. So we should see our power factor change. And so we've got, a non-ideal power factor. We've got, we're pushing 2K VA, of which 1.5 kilo, of which we've got 1.5 kilowatts of real power, and then the balance would then be the reactive power. And we can do negative reactive as well. So this is sort of fully 4-quadrant solution. So ID is providing the real power, IQ is providing the reactive power, and then change the sign is showing if it's positive or negative. And that is everything. So we've got ourselves a little inverter here. It seems to be working well. Changing the ripple of this would be changing the size of that inductor. And yeah, this seems to be a decent solution so far. We can run this with changing frequencies, and it should still hold on to that because this is grabbing those. And then, yeah, it should be all okay. So that's it for this tutorial video. Do check back again for more tutorial videos. This is a 3-phase grid-like inverter with DQ control, where the D and Q references allow us to do pass power back and forth between the two supplies of either real or reactive. Okay, thank you so much for watching. Check back again for more videos.